All right. So last time we were talking about operations on functions, and we had talked about specifically composition of two functions. And we talked about composition of two functions being important because it was part of our definition for an inverse function. And then we talked about some properties of functions called onto, one-to-one, and bijective. And we used those properties to create a framework in order to predict when a function's inverse would also be a function, because we saw in some situations that inverse is a function, in some situations that inverse is not a function. We landed on if a function is bijective, then its inverse will always be a function, otherwise not. So today we're going to kind of continue along in this same topic, but we want to talk about how to determine how to write the function's inverse in a couple of different settings. So let's say we have the graph here. That contains these 3 points. If we wanted to draw the graph of the inverse for this, how would I do that? Yeah, we're just going to transpose the x and y coordinates. So instead of -2, 5, we have 5, -2. Instead of 1, -1, we have -1, 1. And instead of 0, -3, we have -3, 0. Everybody's okay with that? All we did was transpose the x and y coordinates. Now, suppose that instead of this being just 3 graphs, or 3 points, excuse me, instead of our graph being made up by just 3 points, what if this was instead a smooth curve? So our function originally was a parabola, and I notice my inverse function is now like a side-facing parabola, right? Instead of opening up, my parabola now opens to the right. If we were to describe what happened here, what might you say? Right. I mean, I'm talking like from a visual standpoint, though. Andrew? Yeah, so there's a reflection that happens here. So imagine we have this line, y equals x. If I reflect across this line, negative, or 0, negative 3 goes to negative 3, 0. One, negative 1 goes to negative 1, 1. And then negative 2, 5 goes to 5, negative 2. Can everybody kind of see visually what's happening here? Would it help to turn the light out? I don't know how easy it is to see the colors in the light or whatever, but if you decide you need to, just stand up and do it. No big deal. Can everybody see visually kind of the reflection happening now that I kind of draw and illustrate? Notice it's still the same thing as transposing the x and y coordinates, just flipping those locations. So, yes, Anna, of course. Do you notice anything else about F inverse here? Yes, it's not a function. Thank you, Sophie. So we start off with a function. We end up with not a function. And what is was there a way that I could have looked at my f of x here and known before I even found the inverse whether that inverse would be a function or not? What two criteria does f of x need to have in order for its inverse to be a function? Sophie? So, what two criteria does f of x need to have to guarantee that f inverse would be a function? Has to be 1-to-1 and on. Remember this? Those were the two criteria for something to be a bijection. And we said that all the inverse for all bijections would also be functions. So, which one of those criteria is this one failing? We have issues with both of them. Which one is the most obvious one to looking at the graph, though? The one-to-one-ness. And is there an easy way for me to check a graph to see if it's one-to-one? So notice that I have this horizontal line intersects the graph twice, right? What does that tell me about the y-coordinates? They're repeated, so the function cannot be one-to-one, right? And based on the fact that f of x is not 1-to-1, I can say immediately at that point that f inverse is not a function. So again, here we're talking about f of x. Here we're talking about f inverse of x. But that horizontal line test is a really easy, effective way to determine whether the inverse will be a function or not. So again, what does the horizontal line test tell me about f of x? Well, it tells me if it's 1-to-1 or not, right? You're just one step ahead. And what does the horizontal line test tell me about the inverse of f of x? Whether it'll be a function or not. Okay? So this little subtle difference I see students kind of mixing up a little bit, especially on their explanations and using too many like adverbs, or pronouns I should say. Pronouns is the word I'm looking for. So in a case where you're describing what's going on, avoid using the word it. Because there are two possible its. Are you talking about f or f inverse? It fails a horizontal line test, so it is not a function. Right? Like, you're using it for two different things there. It's a bad explanation. I would mark that wrong because it's unclear. If you replace the first it with f of x, and the second it with f inverse of x, that's perfectly correct. So just watch your pronoun usage if you're explaining things. You use the horizontal line test on f of x to tell if f inverse would be a function or not. If you already have the graph of f inverse, you could use a vertical line test on f inverse. Right. We're talking about prediction, so you don't want to actually find the inverse first. If we're talking about making a prediction. If you already know the answer, then it's not a prediction. You know what I'm saying? Okay. Does everybody feel reasonably okay about these finding the inverse from a graph situations? Okay. What if we instead want to find the inverse from an equation, a function written as an equation? So suppose this is our function and we want to find f inverse. Does anybody remember the procedure we used for this? We talked about it last year. So?
F of x becomes y.
Okay, good.
And then just take the x and y.
Okay. Okay. Okay, that's perfectly acceptable. I like to do the swapping of the x and y last, so I get the x by itself first, and then I swap the variables. For the most part, it probably doesn't matter. There's some situations where if you're given a function with a restricted domain, it is more intuitive to understand how to use that restricted domain if you do the swapping last rather than first. But for the most part, it probably doesn't matter. That's a rare instance. But that's just to let everybody know that's the way that I like to do it, is I do the swap last. If you do the swap, like to do the swap first, for the most part, it probably doesn't matter. So, getting the x by itself, I'll add 7 to both sides, and then divide both sides by 3. And then we'll swap the x and y's. Everybody recall doing this kind of a thing? And again, if you wanted to write this also as like x over 3 plus 7 over 3, certainly that's fine as well. Whether you want to write that as a single fraction or two separate fractions, 6 and 1/2 does into the other to me. Either is the same correctness. Okay? So far, so good? So we claim then that f inverse is x plus 7 over 3. How do I know that I'm correct? How would I know that I'm correct? Okay, but that's just a visual check, right? Sam?
You can check a point and then flip the x and y.
But it's got to be true for all the points. Could we check all points from the graph? I like where your head's at, because these are all good ideas. They're not bad ideas, but there's a better one yet that's a little bit more conclusive, that doesn't rely on a visual check, and it doesn't rely on like checking some anecdotal points. It's a check that will work in one swoop for everything. Flip back and look at the definition we gave for an inverse. We would have given this in the last set of notes. We defined very carefully what an inverse was. What did we use in that definition? Joanna. Yeah, you want to use the composition, though, when you say, so what we want to show to see that this inverse is correct is we want to check this. Is that if I do the composition of the function, its inverse, both ways, forward and backward, that each of those give me x. And doing this is equivalent to like drawing the graph and showing that it's a reflection. This is actually how you would do that like rigorously. Because yes, you can graph them and look at them and be like, oh, it looks like a reflection across the x. But to prove it's a reflection across the x is a little bit more difficult there from a geometric standpoint. Algebraically, all we have to do is do this composition twice, which is not quite as bad. So let's do that just to illustrate this. So we'll do this half of it first and show we get x. Everybody good with that plan? So I'll apply my definition of composition and then start by replacing my f inverse of x with its algebraic expression. And then I'm going to write my algebraic expression for f, but every time I had a x, I'm just going to write a parenthesis. Everybody okay with that? So now all I'm left with to do is to simplify. So I have a times 3 and a divides by 3, so those can cancel out. And then I have a plus 7 and a minus 7, So those can cancel out. And I'm left with x. But that's just the first half, right? I also need to check the other direction. I have to do f inverse compose f. Oops. Forgot the f. So if I do that, I'll start by replacing f of x with its algebraic expression. And then I'll rewrite f inverse, but everywhere where there was an x in that expression, I'm going to put a parenthesis. And then inside that parenthesis, I'm going to write my expression for f. Notice if I look in the numerator, I can cancel the minus 7 and the plus 7. And then I can cancel the times 3 with the divide by 3. And I'm left with just x. So what I've shown then is that the composition, each of these two compositions, both give me x. Notice that this is the same idea as we had for addition and for multiplication of just numbers. So let's say we're talking about multiplication. What is the inverse for 3? It's 1/3, right? And I know that 3 times 1/3 and 1/3 times 3 both give me 1. And what was special about 1? That was the identity element for multiplication. What's happening here with composition? When I apply two inverses, I should be getting the identity element back for, in this case, composition, because that's the operation that we had in. So you see that this is really kind of still the same algebraic structure as we saw when we dealt with like multiplying inverses, or if we're talking about addition and subtraction, like 3 and negative 3 are inverses, because when I add those together, we get 0, which is the additive identity. Is that okay there? Let's do another of these algebraic examples with something that's a little bit more complicated algebraically, because that linear function that we just gave you guys was pretty straightforward. There can be some tricky things. Let's make sure that we've talked about how to deal with some of these more trickier ones. So let's say we have this rational function, h of x, and I'm looking to find its inverse. So the outline of what to do that Sophie described earlier is the same thing that we're going to do. So we'll replace the h of x with just like a y equals. And then we're going to get the x by itself, and then swap the x and y variables. It's the getting the x by itself part that proves to be a little bit more complicated in this problem. Does anyone have a suggestion as what I'd want to do first to get the x by itself? Yes. Bella. Yeah, that's exactly what I would do as my first step. The other way you could have said that same information is to say we'll cross multiply. Think about it as y over 1, and then you can do that cross multiply thing. You're describing the same process either way, but that is the first thing that I would do. So if I multiply both sides by 5x minus 8, I get this. Everybody agree with that? What might we do next? Distribute the y. Good. Yep, let's do that. Okay. Now what? Yep, thank you. Again, the goal is to get the x by itself, right? So let's get the x's all on one side and the stuff without x's onto the other side. Does that sound okay to you? So we'll just subtract 2x over, and we'll add 8y over. Everybody okay with that? That seems like a reasonable next step if we're trying to get the x's by themselves, is to at least get them all on one side. Andrew? Yeah, so this becomes the part that's often like easy to overlook, is if I look at that left-hand side now, each of those two terms has a greatest common factor of x. So I can factor that out. Everybody agree there? And now I can divide both sides by that 5y minus 2. And then when I swap the x's and y's, we're there. So my inverse then is 5 plus 8x over 5x minus 2. Should we check to see if these are inverses? This gets a little bit messy, so it might be a nice review of how to deal with like a complex fraction to go ahead and do that. What do you guys think? Probably worth doing if you don't really remember what we mean by complex fraction. Okay. So I'm going to do both of the compositions here at the same time, basically. Is everybody okay with that? So we have here 5 plus 8x over 5x minus 2. And on this one we had 2x plus 5 over 5x minus 8. And so now I'll go ahead and plug this in. So everywhere where there was an x in my f, I'm going to put that set of parentheses. And inside that parenthesis, I'm going to write that. Similarly over here, I'm going to write my f inverse, and everywhere where there was an x in my f inverse, I'm going to put a set of parentheses, and inside that set of parentheses, I'm going to write my f. Is everybody okay to hear? Okay, I'm going to pause here for a second because I see a lot of people still writing, and the next parts are kind of tricky, so I want you to make sure we're listening and watching and not just trying to copy down stuff. So I'm going to stall here for a minute or two. Notice that what we have in each of these two situations is something called a complex fraction. By that I mean like I have a fraction with fractions inside of it. Everybody see that? So the easiest way to simplify something like this is to multiply by 1 in such a way that I eliminate the fractions inside a fractions thing, and I'm left with just one fraction. So if I look here, I have the same denominator in both the numerator and denominator here, right? So what I'm going to do is I'm going to multiply the top and bottom by that denominator. When I multiply to the first piece in the numerator, the 5x minus 2 in the denominator cancels with the 5x minus 2 I'm multiplying in, and I'm left with just 2 times 5 plus 8x. But I also still have to multiply it to the 5. And I'll do the same thing in the denominator. And what I'm left with now is just a single fraction, right? I've gotten rid of the fraction inside a fraction business. Can everybody see that? And from here, the simplifying becomes much, much easier because I only have to deal with one fraction instead of like multiple fractions inside of fractions. That's a nice little simplifying trick when dealing with these complex fraction situations. So I'm going to do the same thing over here and multiply both the top and bottom of this one by 5x minus 8. Is everybody satisfied with that there? And you can see here probably pretty quickly why I wanted to do this as an example, because the simplifying here is not trivial, like it's kind of a pain in the butt. And we still have a lot more to go, right? So let's distribute all of this stuff out. So, you know, all of this. Let's multiply it all out. And at this point, I'm going to let you guys kind of finish this one up here on your own, but should be okay. I'm going to add a little bit to the homework set here on Power School later this afternoon, so keep an eye out for that. So we'll have a little bit for you guys to do on tomorrow. We'll meet again tomorrow, right? You're welcome. You're welcome. Have a good day, guys.
I have a quick question. On the homework quiz,